All right, so in this lesson, we're going to learn about the composition of functions, and not really learn it, we're going to review it, maybe take it to the next level. So we know function notation. We use f of x. Okay, so we have a function here, 2x minus 3. If we're evaluating, you would write it as f of, in this case, 5. So that just means we put in 5 everywhere there's an x and evaluate. So 10 minus 3, that comes out to be 7. We can do it with numbers, we can do it with variables. So if I do f of c, that means everywhere that there was an x, it now becomes a c. They're not like terms, can't combine it, 2c minus 3. Moving on, I can put in, more involved expressions. So 4a, again, replaces the x. So it's 2 times 4a, or 8a, still minus 3. And then on the last one, 2 times 5x minus 1 minus 3. So that's 10x minus 2 minus 3, or 10x minus 5 when you simplify. All right, now that's just function notation. You've dealt that many times. Now we're going to deal with composite functions. So for composite functions, we plug a value into x into a function. Then that output gets plugged into another function. Sometimes back into the same function, sometimes into a different function. Plus, excuse me. Okay. So we plug the output y into one function, back into another. Okay, it's called a composite function. So let's see what we got here. We got g of x equals 3x plus 1. And then we're going to do g of 2 equals c. Find c. So if g of 2, so g of 2 is 3 times 2 plus 1. That's 7. That's equal to c. So now if we want to do g of c, that's the same as g of 7, which would be 3 times 7 plus 1, or 22. Okay, so notice that our output became the input. The 7 became the input into that same function. Now, when you deal with composite functions, there are 2 different ways we can write them. We can see f, parentheses g, parentheses x, and then close them both. Or we can see f with the composite symbol. It's like a little circle of g, and then parentheses with an x. We read both of these as f of g of x. Notice I never said multiplication at all. I didn't say times. I said f of g of x. Okay, when you work with composites, you start on the inside. Okay, or the far right. So if you're given f of g of x, we're going to start with g of x, and then use the answer from g of x and plug it into f. All right, so if we've got f is 3x minus 5 and g is 2x squared plus 1, we want to do f of g of 3. We're going to start by doing g of 3. So that's 2 times 9 plus 1, which is 19. Then that goes into f, and we do f of 19. So 3 times 19 minus 5, which will be 57 minus 5. So 52 is the overall f of g of 3 answer. Okay, here we start on the inside. We do f of 3. We read this as g of f of 3. So we start with f of 3. So 3 times 3 minus 5, which is 4. 4 now goes into g. So 2 times 4 squared plus 1. 16 times 2 is 32, plus 1 is 33. So the overall is 33 there. Okay, now we can use the same function like we saw up above. We start with f of 4. 12 minus 5 is 7. And now 7 just goes back into the same exact function. So I'm not switching functions this time. So 21 minus 5 is 16. We can use composites to come up with equations as well. So we're going to use these from above still. F of g of x. So f of, for g of x, that is 2x squared plus 1. That means this quantity is going in everywhere there's an x in the f function. So 3 times 2x squared plus 1, close it, minus 5. If we distribute and combine, this will be 6x squared minus 2. All right, and then over on this one, g of f of x, well, f of x was the 3x minus 5. So we're going to do 2 times 3x minus 5 squared. So 3x minus 5 squared, 9x squared minus double distribute, so 30x plus 25. Now if we distribute the 2, and then lastly just combine with that 1, 18x squared minus 60x plus 51. Okay, so what we see here is that order matters, right? Those are completely different. We can't just, f of g of x and do whatever order we'd like. We have to go in the order that it says, because if not, those are completely different, f of g of x and g of f of x. Okay, a couple new functions here, 4 new functions in fact. We're evaluating, so k of h of 2, start with h of 2, so that's in this one. I get 1, that becomes, the input into k. So it looks like that's going to be 10. Okay, moving on. So now we start m of negative 1. So negative 3 plus 2, negative 1. That goes into the h function. Looks like negative 5 is the output. All right, p of x. So p of x is the radical. That goes into k now. I'm going to come down below it because we're going to have to write a bit. Oops. So if we square the square root, I just get the radicand 3x plus 1. Over here, just going to have a coefficient of 4 on that radical. So if we simplify, I'll have 4 times square root of 3x plus 1 plus 3x, and then plus 6, because I can only combine the 3 and the 5, or the 1 and the 5, sorry. So that is our function. Okay, we've got a few here different. We got a piecewise graph. We got a table for g, and h is this piecewise. K is a quadratic function with a horizontal translation. Horizontal translation of 2. So remember, that's going to be on the x. So x minus 2, since it's quadratic, squared. And then a vertical translation minus 3. So we can write an equation for this. All right, so I'm going to shrink this down, I think, so I can see it all. All right, what do we got? F of g of 3. So if we start with g of 3, there is no 3 in those inputs. So this is not defined. We actually can't figure this one out. Can't make it up. Okay, we got to go with what we know. H of f of 8. So if we start with f of 8, that's on the graph. So f of 8, what comes out of that is negative 1. Then we're going to do h of negative 1. That's over here. Negative 1 falls less than 1, so we'll do absolute value, negative 7 minus 3, so it's absolute value of negative 10, or overall output is 10. All right, next one, g of k of 0. So start with k of 0. If I put 0 in there, I'll get negative 2 squared minus 3, so 1. Then I'm doing g of 1. Up here in this table, I have no inputs of 1, so again, not defined. All right, f of 2. So go to the graph. When the input is 2, the output is 1. The other one has an open circle, so that doesn't exist for it. Now we do f of 1, input of 1, output is 4. Okay, keep it rolling. G of h of 1, so h was that piecewise over here. H of 1 is -4. If I do g of -4 in my table, input 4, output pi. Oh, ooh, this is a big one. So we start all the way at the far right, k of 3. So k of 3 would be 1 squared minus 3, or -2. H of -2. -2 is less than 1, so -7 minus 6. It's going to come out to be 13. Work backwards. F of 13. On this, it doesn't even go out to 13, so not defined. We can't assume that it keeps going anywhere. There's no arrows, so it's not defined. All right, so now we can find the domain of our composite functions. All right, so we can create these composite functions, f of g of x, g of f of x, and then what's the domain of that? All right, so there's a couple rules here. First, you have to find the domain of g being the input function. Then 2 and 3 kind of go together. It says find the domain of f, excludes those inputs x from the domain of g for which g of x is not in the domain of f. Basically, find the domain of f of g, the composite function. And then you must combine the two and include where they overlap. Okay, so only what's common to both the input function and the overall function. So let's look here. The domain of g of x, since it's a radical, we would take the radicand. That has to stay greater than or equal to 0 in order for you to have real solutions come out of that. All right. Domain of f, well, that's a quadratic. That would be all real numbers. All right, let's look at f of g of x. So we're taking g of x. We're going to do f of the square root of x, which means we're taking the square root of x and we're squaring and adding 4, which means for f of g of x, we get x plus 4. That's our overall. Now, that's a linear function. So the domain would be all real numbers. So if we are to combine the input and the overall, then it is going to be simply when x is greater than or equal to 0. Because if for g we can only have greater than or equal to 0, that means for the overall we can only have greater than or equal to 0. All right, so similarly here, find the domain of f of g of x. So the first thing I would look at is the domain of g of x. So that means 9 minus x squared has to stay greater than or equal to 0. Well, if we factor this, that's 3 minus x and 3 plus x. I'm going to find my zeros. So now we're going back to a quadratic inequality. This is a quadratic that would open down because it's negative leading coefficient. So I want to know where is it greater than or equal to 0. That's in between these roots. So from -3 to 3 would be the domain of g. All right, let's actually create f of g of x. So we're doing f of g, which is the square root of 9 minus x squared, which means we're taking that, we're squaring it, and subtracting 9. So if I square it, I just get the radicand. And when that simplifies down, that's f of g of x. So it's a negative x squared, which the domain of this would be negative infinity to infinity. So then the domain of f of g of x would be the combination, and what is in overlapping between the two, and that would simply be from -3 to 3. Okay, one more. Let's throw a rational function in here. So domain of f of g of x, that means first I need the domain of g, which that's a line, so it's all real numbers. All right, let's create f of g of x. So we're doing 1 over 2x plus 1. All right, now this is rational function, so a little review from Unit 1. The domain of this would be anywhere that the denominator is not equal to 0. So it means x can't be -1/2. So now if I combine these two, the domain of f of g of x, the composite, would be anything that's not -1/2. There we go.